What happens when your reliability data is small, skewed, or simply refuses to fit a bell curve? You reach for a non-parametric test. And one of the most powerful tools in that category is the Wilcoxon test. The t-test has one critical assumption. Your data must be approximately normally distributed, or your sample size must be large enough for the central limit theorem to compensate. But in reliability engineering, sample sizes are often small, distributions are often skewed, failure times follow Weibull, not Gaussian. When you force a t-test on non-normal data, your p-values become unreliable. You may declare a difference that does not exist or completely miss one that does. The Wilcoxon test actually comes in two forms. The first is the signed rank test, which you use when you have pair data, such as before and after measurements on the same unit, or when you want to test whether a single sample has a specific median. The second is the rank sum test, also known as the Mann-Whitney U-test, which compares two completely independent groups. Same underlying principle, different application. Both assumption-free. Both tests share one elegant idea. Instead of working with raw values, you rank them. Take your measurements, sort them from smallest to largest, and assign ranks starting from 1. If two values are tied, they share the average of their ranks. Now, instead of asking how large is the difference between values, you ask how different are the ranks. This makes the test completely immune to distributional shape. An outlier at 200 newtons gets rank 8, the same rank that 45 newtons would have received. The math only sees order, not magnitude. The signed rank test works like this. You have paired measurements. Connector retention force before and after 200 thermal cycles. First, calculate the difference for each pair. Then rank the absolute values of those differences. Then reattach the original sign, positive if the value went up, negative if it went down. The sum of positive ranks is W minus. The sum of negative ranks is W minus. Your test statistic W is the smaller of the two. If most differences go in one direction, W will be very small, and that is your statistical evidence against the null hypothesis. In this example, W equals 4, which is at the critical threshold for 8 pairs at an alpha of 0.05. Thermal cycling significantly reduced retention force. The rank sum test is your tool when comparing two independent groups. Say you are evaluating insertion force from supplier A versus supplier B, each with 8 measurements. You pool all 16 values together, rank them from smallest to largest, but keep track of which group each value came from. Then you sum the ranks for each group separately. If the two groups perform similarly, both rank sums will be roughly equal. If one group consistently produces higher values, its rank sum will be much larger. The Mann-Whitney U statistic formalizes this logic, and the p-value tells you whether the separation in ranks is statistically significant without a single normality assumption. Let's walk through a real case. You are qualifying two connector suppliers for an electric vehicle program. Both are tested for insertion force, 8 measurements each. Supplier A averages around 40 newtons. Supplier B averages around 48 newtons. The sample size is small, and a Shapiro-Wilk test flags non-normality in supplier B's data. You would not trust a t-test here. After pooling and ranking all 16 values, supplier A dominates the lower ranks, and supplier B dominates the upper ranks. The Mann-Whitney U statistic equals 0. The p-value is less than 0.001. You reject the null hypothesis with strong confidence. Supplier B produces a statistically superior insertion force, and you have reached that conclusion without assuming anything about the underlying distribution. How do you decide which test to use? Start with one question. Is your data normally distributed? If you have 30 or more observations, the central limit theorem generally protects you, and a t-test is usually appropriate. If you have fewer than 30 observations, run a Shapiro-Wilk normality test first. It is the most reliable option for small samples. If normality fails, and in reliability engineering it often does, ask one more question. Is your data paired or independent? Paired goes to the signed rank test. Independent groups go to the rank sum test. That is the complete decision tree. 2 questions, 3 possible tests. No guessing. Non-parametric does not mean inferior. It means honest. When your data cannot support the assumptions of a t-test, the Wilcoxon test gives you a valid, powerful, and interpretable result without compromise. Remember 3 words. Verify your distributional assumptions before choosing any test. Choose the right Wilcoxon variant based on whether your data is paired or independent. And conclude with confidence, knowing your p-values are actually trustworthy. In reliability engineering, the strength of your conclusion is only as good as the test you chose. Choose correctly.